Go for it.
The diagram below shows two parallel horizontal plates held 2 centimeters apart.
Great.
The top plate is held at a potential of 1,500 volts.
Okay.
And the lower plate is earthed.
Okay.
A very small oil drop of mass 3.06 times 10 to the minus 14.
3.06 times 10 to the minus 14
has
kilograms?
Yes.
Yep.
Which has a net negative charge, is held in equilibrium and prevented from falling under gravity by the upward force of the electric field
Okay.
of the plates. What is the value of the electric field between the plates?
Okay, so E equals V over D, which equals 1500 over 0.02, which equals 1500 over 0.2, which is 75,000 newtons per coulomb. And the second part is determine the charge.
The number of excess electrons.
Yeah, okay. So look, the total, the weight, mg, must equal the force provided by the electric field, which is EQ. Isn't it?
Yes.
Yeah. So therefore, Q equals mg over E. However, it's not the charge that they want, but the number of electrons. So how would we convert this into number of electrons?
Q divided by...
Yeah, Q divided by the electron charge.
Yeah.
So the answer would be 3.06 times 10 to the minus 14 times 9.81 over 75,000. What was the value for E? 1 point, no, something.
I don't have my sheet.
E, whatever it is.
I'm just going to use the...
Calculator, yeah. Okay.
What is it? Charge electron.
Easy peasy, guys. How come you didn't do it at home? What has you busy these days?
What's that charge of the electron? Put 1.602 times 10 to the minus.
That's it.
It says so there.
Proton, electron, neutron.
No, that sounds like the mass. It's like 27 or something.
It's 1.602.
No, it's micro. The
Oh,
prepared
no,
of
the,
micro.
What?
yeah, the U kind of with a...
What are you looking for? The E
The charge
constant.
of an electron.
Yeah, which is the symbol E on the calculator constant list, which is constant like...
It's just E?
Yeah.
24.
24 point...
25.
Oh. Electrons. Yeah, easy peasy or not? What's the story?
Easy.
Yeah? Is okay? No?
Or
Or
draw a
is it?
sketch diagram of the electric field lines around an isolated.
Boring. What, of an isolated what now?
Draw a sketch diagram of the electric field lines around an isolated electron showing the direction of the field. Easy.
There we go.
What I use it?
Anything else? Do
What
they want
is-
the equipotential lines?
What is the value of the electric field strength at a distance of 10.8 meters?
Wait, is this the second question?
It's the same. Yeah.
I thought we deleted the second one.
No, it's part C.
Oh, okay. So what do they want the electric field strength on? What?
At a distance of 10.8.
Okay, that's boring too because that's 1 over 4 pi epsilon 0. Is it of an electron?
Yeah.
Q over and the distance?
10 to the minus 8 meters.
Okay, blah blah blah. Easy peasy.
What? I mean 301. That won't do.
Did you get this right? You got this? Yeah.
I'm going to type it in. 4 constant 32.
What's the electric field strength term?
Let me see. 1, 2, 3, 4, 5, 6. 144 to the times 10 to the minus 6. No, times 10 to the 6, sorry. So, mega, no? Yes. Maybe you should put it up.
Yeah. Okay. Yeah. Okay. You still need to do your physics homework, even if it is one question. In fact, it's more important when it's only one question because you have less to practice. All right. Will we continue with magnetic fields?
Yeah.
Yeah. So, what slide did we finish on last time?
Solenoid.
Oh, it's solenoid. Yeah. Okay.
Beautiful. It's alright.
Did we? So which slide did we finish on?
Solenoid.
This one. Yeah. Okay. So we're continuing from here then. Okay. We saw two things that may need clarifying. That is, what was the last picture, and how can we tell which way the magnetic field, I should say, will point around the wire and the current. So,
You do that.
yeah, that leads us into the next one. So look, there's this rule called the right-hand rule. If you have a current, a charge moving, you hold the current and you put your thumb in the direction of the current. Then your fingers are the magnetic field, with your right hand. So as I'm pointing to you, I can see that the magnetic field will be going this way, around the current. Do you remember that we said when a charge moves, it makes a magnetic field? And when the charge stops moving, it stops. But it always has an electric field. Yeah? Okay, so you'll need to make some note of this. This is called the right-hand rule. Well, I don't know if we can draw this. Make some kind of note so you can remember this rule.
Take a mental screenshot. This rule is pretty easy to remember.
Yeah, but what's going to happen is in the exam you'll be sitting there going, wait, was it the right or was it the left?
I remember when we were doing a physics exam,
Yeah.
and we were doing motors and
Yes, we'll do that
so
too.
everyone was
Yes.
like,
Yes.
Yeah, with that.
the exam, they're like trying to remember.
But are you going to remember if it's right or left?
Yeah,
Are you sure? Because we're going to have 3 of these rules.
that's fine.
Alright, we'll see.
So which way is north and south?
North and south.
Yeah.
Oh, no, we'll get to that later. That's it. Maybe actually later today. Okay, can I continue? You have some kind of note made? Yeah? Okay. So, back to solenoid for a moment. What's the definition of a solenoid? So what would we say? Is it?
Wound wire. Or wire wound around.
Yeah, a coil wound into a helix. I gave you that word last time, didn't I? Helix, yeah. Yeah. Actually, do you know what? I should have really said in the definition, a solid... Actually, I don't even know technically if it needs the current. No, actually, I think that might just do. Yeah. Okay. Okay.
So it doesn't need to have like an iron core to use.
Doesn't need to have it, no.
Why does that help with the magnetic field?
I think because the iron core permits the magnetic field through it more easily than air would. I don't want to say it's a better conductor of magnetic fields because that's the wrong word, because there's no current. But it's in that the word is permissibility or permeability.
Yeah.
It facilitates the magnetic field that's formed
Yeah.
better than empty space would.
Wouldn't it get heated? Because I've seen
Yeah.
videos.
Yeah,
of
yeah, it would.
people-
Yep. Yep, it get heated. Yeah. So that represents a waste, an inefficiency. Okay, we have this already. So we've actually not talked about the units. We've been talking about magnetic fields, and we've not said anything about the units we use. So far we've said nothing about the units. We need to measure how strong the magnetic field is. And we call that the magnetic flux.
Where?
Yeah. The magnetic flux, phi, over a particular area of space. Oh, okay, well, do you know what it is, Zach?
Isn't it? I know it's a Newton per. No.
The definition of this is extremely difficult. And I was looking up the proper definition of it, and I was thinking, wow, okay, this is not the definition on the IFY. But I couldn't find an exam question where they asked for the definition of a Weber. So after much searching, I found what I felt was the suitable definition for this level of the course. The magnetic flux over a particular area of space is the number of magnetic field lines passing through that area. The SI unit of magnetic flux is called the Weber. So I'll just give you, which is the same as the volt second. Now before you write that down, I'll just give you a quick picture. So suppose I have north here and south here, and I have a magnetic field like this from north to south, and I'm looking here at this piece of space. Let me just call this X, for example. The magnetic flux at X would equal 2 Webers. Why 2 Webers? Because I have 2 field lines. Now, if you think deeply enough about this definition, you realize it doesn't really make any sense. But so it's not a proper definition. I welcome you to look at the proper definition. It is well beyond the scope of this course. It would only be suitable at a second or third year of university. So this is what I could find as a sort of high school level definition. The Weber is a way to count the field lines. Okay, but it's not the proper definition. But it's what we have for this course. And the unit actually, interestingly, is the same as the volt second. Now I have, I don't know how you would prove that. I don't know. I don't know. Apparently it is the same as the volt second.
What is a volt second?
It's a Weber. It's a field line. Alright, write this down anyways.
Tried it hard to make it into something tangible.
Yeah. Anyways, they don't ask for this in the exam.
Yeah.
There's something else they ask for which comes up. Okay. Have you got that? Dorian, you have that definition? Gina? Yeah, you have that? So, one small problem with this definition is that it depends on how big the area is. For example, if I was to look at this piece here, let's just call it Y, what would be the magnetic flux at Y? 1 Weber. So we don't really like this definition because it depends on the size of the area. So what could we do to make this a bit more sensible? Well, we could look at the flux per unit area, per meter squared. And that gives us the next definition, which is called the magnetic flux density. And this is the amount of magnetic flux per unit area. So go on, have a guess at what the formula is for B. Yeah, the flux.
Pi over
We
m
Yeah.
meter squared, so that would
Yeah, over area. And the unit would be a Weber per meter squared. And the Weber per meter squared is called after our good friend Tesla T. A Tesla T is 1 Weber per meter squared. You know, everybody knows Tesla, right?
The cars.
Like the cars. Yeah, like the cars. Yeah. Yeah, I'm sure the cars are named after Nikola Tesla. It has to be, yeah.
They even have like the T.
Do they?
Size.
Right. Interesting. Yeah. The B for the magnetic field is the nearest thing we have, which is like the E for the electric field.
Yeah.
It's the most comparable thing to the electric field's E. Because it's also a strength, you know? A higher value of B would basically mean a stronger field at that point. Yeah?
I find it difficult to find, like, B and E is constant between parallel plates, but like for a point charge, it's not. And like magnetic goes around in like a current wise, so
The
there's
B also
dimension.
varies. The B also varies. It depends on the position. So, just like the electric field, if you're further away, it'll be smaller. Now, it is well beyond the scope of this course to calculate the flux. It'll just be given to us. But we understand that it'll be a smaller number the further out we are. I can't remember the formula, but it decreases. Zach, the flux here decreases much faster than the electric field does at a distance.
Yeah.
All right, continue. Yep.
How did did someone even discover that?
Well, I think, maybe it was Faraday who first discovered this. Faraday was, you know Faraday? I think he was the first person to work on electric fields and magnetic fields. You know.
Yeah, he did the motor and
He did do the motor, didn't he?
generators.
Yeah, so like he did all the kind of groundwork on this.
Yeah.
Faraday cage, yeah. Okay, so, do you have that definition? Yeah. So, we know a moving charge will produce a magnetic field. And by using the right-hand rule, we can know what the field looks like. So if I have a charge, a proton, and it moves from me to Zach, the magnetic field will be spiraling around like this as it moves towards Zach. Okay. But what happens if I put a big magnetic field inside this room? So imagine there's a north and there's a south, and I have my little charge moving, and my charge has a magnetic field.
Is it the same for positive and negative charges?
No, because if a negative charge moves from me to you, then we say the current is going this way, so it'll be the other direction.
So it's in the direction of conventional current.
Yeah, conventional current. Yeah. So imagine my little charge is moving and it has a magnetic field around it, but it's inside a bigger magnetic field. Well, we know that when north meets north, what happens? Repels, and when north meets south, it attracts. So in other words, the charge will respond to being in the magnetic field. It will interact with the magnetic field, and the charge will move. We know this: north repels and south, and so on. So there is a way to calculate the force on a charge Q in a field of density B by moving at velocity v. Now, why is it important that the charge is moving at a velocity v?
Constant
Mm-hmm.
as direction.
Mm-hmm. Well, if the charge particle wasn't moving, would it be making a magnetic field around itself?
Yes.
It wouldn't be, and so it would not interact with the larger magnetic field. So that's why it has to have a V. Yeah? So the formula is actually pretty simple. To calculate the force on the charge in the magnetic field is equal to QV times B. Now that times That's a special multiplication because the v is a vector and the b is also a vector. So although the calculation is q times v times b, there is a way to work out the direction here if you have two vectors multiplying each other, which we haven't talked about yet. The x is a special multiplication called a cross product. This is the cross product of vectors, where the result is found using what's called the left-hand rule, which is on the next slide. So, just before you go on to that, just to be clear, maybe there's a north, maybe there's a south, and maybe here's a little charge. And this charge, as it moves, it will make a magnetic field. And that field will interact with this field, and it will cause it to experience a force. So, this is how you can calculate how big the force is. If the particle is moving faster, there's more force on it. If the particle has a bigger charge, there's more force on it. And obviously, if the magnetic field is stronger, there's more force on it. So it makes perfect sense. Once you write this down, we'll have a look at what's called the left-hand rule, Fleming's left-hand rule.
Why would the magnetic field get stronger the faster it's moving?
Beats the heck out of me.
Because it cuts through more lines in second reason.
Well, no, I don't know. Are you asking me why the force is bigger, Zach, or why the magnetic field that it generates?
Well, isn't that what it implies if the force is greater?
Yeah, I suppose it does, doesn't it? You said, Dorian, because it cuts through more field lines. Yeah, okay. I'll go with that answer. I am not 100% sure if that's true. No, sorry, Dorian, I'm not sure if that's true. I think what's happening, Zach, is that the faster the particle moves, the stronger is the magnetic field around it.
Why?
That's what particles do when they move, it seems. They make a magnetic field. They move faster, they make a stronger field.
Okay.
It kind of has to be like that because there's no magnetic field when it's at zero.
Yeah.
So it can't be that it's at, it can't just be it's at rest, there's no field, and then it moves and there's a big field. There has to be some graduation to it, you know. So
It's dependent of its velocity.
yeah. But it's not. It's just the way they behave. When charges move, they make magnetic fields. It's just a fact about charges.
Is it like a 1-to-1 ratio, or would it be more like a?
Yeah, I think it's linear. Yep, I'd say it's all linear. Yeah. Okay, continue. Yes, do you have that? Now, I said we can calculate the direction of the force, okay, using something called Fleming's left-hand rule. So I'll give you an example. Now, everybody will have to look at my example, okay? So let's say here is north, and then here is south, okay? So which direction is the field? The field goes from north to south, so the field is going that way, okay? Now let's say I have a charge moving from me to Zach. So the charge is the current, so that's going towards Zach. So I need to take my left hand, have the field going to the door, the current pointing to Zach, and then the force on the charged particle is upwards. So if I have a little particle and I throw it at Zach, here, catch my proton. So as I throw the proton at Zach, there will be an upward force on it. So it deflects up. It swings up as it moves towards Zach because it's an up force here. Yeah.
That was more what I wanted to ask. If it was a proton or electron, the magnetic field would be in the same direction.
No. If I throw an electron at Zach, guys, if I throw an electron at Zach, which way is the current?
It's downwards.
Which way is the current?
Oh.
Towards me. So in my left-hand rule, I would have to do this. Because the current is this way, but the field is still this way. So the force is this way. So if I throw an electron at Zach, it will deflect down.
But that's with convention, because if the electron actually moved this way,
Hmm?
then the magnetic field is the opposite way.
The magnetic field is the opposite way.
To,
Yeah,
than to a proton.
yeah, and that's why it deflects down. Okay. Can you draw Fleming's left hand in your notebook?
I'm just going to get a tattoo on my
Fleming. Fleming has the most famous left hand there is. Okay, left hand. Fleming's left hand.
beautiful hand.
Got it? Gina? Got it? Yeah. Continue? Is this okay, the left hand rule? Yeah?
I think my hand is a little bit messed up. What do you think?
Show me, what did you draw?
No, it's okay. Mine is worse.
Alright, whatever. Okay, continuing. Right, here's a very simple one. A bar magnet has a flux of 2 Webers, and we're looking at a circle of radius 1 centimetre. What is the flux density? So, what's the formula? It'll be 2 over pi r squared. So you've got a circle, and you've got 2 Webers going through it. What's the flux density in Tesla?
2 over pi squared.
Are you sure, Zach?
I don't know.
It might be 1 centimetre.
Ah.
Oh, centimetre. Haha, right. So what do we get? How many Tesla here?
6,366.
So 6 kilotesla, is it?
Yeah.
Weber is actually a big unit. It's a very big unit. I think this would be an extremely strong magnet, like industrial strength. Usually it's milliwebers. Okay, continue. Yeah. A proton moves towards the east in the Earth's magnetic field. What direction is the force due to the field? Yeah, well, we really have to think about this, okay? So, let's have a good think about it. Santa Claus, penguins, Mecca, America. Okay. So, the proton is moving towards the east. So that's the field. Sorry, that's the current.
Yeah, but north is actually south, and south is actually.
I know, we're getting there, Zach. Just relax. Okay, so this is the North Pole where Santa lives, but it's not the north of the magnet, is it?
No.
The magnet's north is really here
So
and south. So the field is going this way, north to south.
north to south.
So using the left hand, let me see.
Index upwards.
That is like this,
Yes.
out of the page.
Current.
Yeah. I'm looking at my laptop screen. I think I have it matched up.
Yeah, it's towards
Yeah.
you.
Towards me, out of the screen.
Yeah.
So, by the way, the way we represent out of the screen is with this symbol.
Oh, yeah.
This means out of the screen, like towards the viewer. And does anyone know what the other one is?
Next.
Yeah, the plus, the X, yeah. This is in. Yeah. So the answer is this one, out. So what would that mean if we were looking at the proton? Which direction is east?
East here.
Well, wait.
I think it's
That
We-
that
we-
way,
no.
around that
No,
way.
none of you are Muslim.
That's wait, what?
That way.
That one?
How did I
That
hear?
way.
I didn't know you were Muslim. You know which way Mecca is?
Yeah.
Which way is it? This way? East?
So
Where
it's
is the one that is?
well, north is that way, so east is that way, around that corner.
North is that way.
Yeah, north is that way.
Oh, it's that way. Okay, so east is about that way.
That way.
Okay, so if my proton is moving to the east,
It's moving
what direction will the force?
towards yourself.
No, now we're in three-dimensional space now. So look, it's moving towards the east. Here it goes.
A proton.
The proton. What will the force cause it to do?
What's it to do?
Yeah, it's like
Move this way.
oh, that's it. Yeah, as it moves towards the east, it will be deflected up. Yeah. No, you don't look happy with this at all. Because here, here in this picture, this is just me looking from the sky at the situation I'm describing, which is the proton moving towards the east.
From what is your observation, point of observation, which direction?
This is me looking,
That's from up.
yeah, that's from
So
the
you
sky,
have
looking
You have to
down.
put it like that, north, and then.
So out of the page here would represent an elevation moving upwards, because this is me looking down from the sky.
Okay.
Yeah?
North, so would be that.
Yeah, so it'll move to the east and be deflected up by the Earth's magnetic field. Yeah,
So
it's okay.
Yeah.
let me ask you, if north is south and south is north,
Hmm?
west is east,
No,
or not?
no, it's not. It's not. All right. Okay. Last question here. An electron enters a magnetic field and then experiences a deflecting force. The magnetic flux density at the location of the electron is about 250 millitesla. The electron is moving at 1/10 the speed of light. What is the acceleration of the electron due to the field? No,
Acceleration.
Huh? What's wrong? 1/10 the speed of light.
QE times B.
No, actually, I want to change this a little bit. So I'll draw it for you, okay, to make it a little easier. This is what's happening. Look, here's a particle. What did I say it was? An electron.
Moving at a 10 of C.
Now, what happens is, I didn't say this in the story, but you know this from your chemistry spectrometer.
Yeah.
It moves in an electric field and it accelerates. And so now it's moving here and its speed is 1/10 the speed of light. Okay? Then it enters a magnetic field. North, south. So tell me what will happen when it enters the field here. Well, let's use our left hand here. Oh goodness.
That's why you see everyone on the exam. Not really.
Yeah, that's what you do.
Downwards.
The current, which way is the current? Left. Because it's an electron.
Yeah, like
Which way is the field?
north to south.
Out of the screen, isn't it? So, up,
Like this, isn't it?
isn't it?
Wait, what?
Hang on.
North to south.
Current is
Index.
Current is left.
left.
Yeah, then it's up, yeah.
Current is left.
Current towards
And field?
the back.
Field is
Index.
in or out?
Yeah.
It's out.
Yeah, north to south.
North to south.
Oh, okay.
Yeah.
Yeah. And so which direction is the force?
Up.
Up. So when this particle enters the magnetic field, it will be deflected up. Now you know this from chemistry.
No acceleration will change because it's perpendicular.
No, it'll accelerate here. It's accelerating here. So I have two questions for you.
But it's in the perpendicular direction.
1 second, Zach. Question A is I want the acceleration. And B, I want the radius of deflection. So this is going to deflect up. So what type of motion?
Circular.
It's circular motion.
Didn't we say that it was?
I thought we said it was up.
Yeah, but that way.
Up. This is up.
Oh no, yeah.
Don't confuse me, man. This is up. Going up. Right. Do we understand what's happening here?
Yes.
You did this in chemistry. This is the spectrometer.
It's flexing.
It deflects. So we want to calculate the radius of deflection. Now, in order to do that, we first have to calculate the acceleration. Now, let's calculate that together. So, we have our formula. It's F equals QVB, right? But what is the formula for F? That's A equals QVB. So, what's the A? Do we know the Q? Yes. Do we know the V? Yes. Do we know the B? Yes, I gave it in the question. It's 250 millitesla. And do we know the mass of an electron?
Yes.
Yeah, so give me the A.
Shift 7. Charge of electricity.
What was what's the thing?
23.
The V is the
Oh,
velocity,
that's the
which
velocity.
it's here, Dorian,
Okay.
1/10 the speed of light.
I put the notation.
Where is C?
It might be C0 on the calculator.
Why is there 3 of them?
I think there's like maybe one in a vacuum, one in something else, and so on.
Are you sure it's going up?
So it's
I'll leave me alone,
No,
Diego. I'm
really.
pretty sure it's going up.
Look, if it's going this way,
C0?
and if it's going down,
Okay.
Excuse me. Right, left hand.
yeah,
V is times
Field is going to you.
yeah.
Current is going left. It's an electron.
Yeah, no.
V is times 10 to the minus 3, right?
Yes.
Yes.
Syntax error. 1.32.
Are you okay, Gina? Okay. You don't like this. What's confusing you? You can seem confused too. Is it because it's up? You think it should be down? Okay.
Field.
Right. Put your hand. Okay. This is the field. This is the current. The field is north to south. So
What's this?
that's going to you. It's going from north to south. So it's going to you. So I need to turn my hand this way. Okay. Now this is the current. It's either going there or maybe it's going there. Let's have a look. The electron moves right, so the current moves left.
Conventional current.
Yeah. Yeah, okay.
So 1.32 times 10 to the 18.
1.32 times 10 to the 18 meters per second squared. Yeah. Now, I know for a fact that the time it spends accelerating must be extremely small,
Yeah.
because such a large acceleration would have it going too fast, too quickly. So it must only be accelerating for like a microsecond or something. Anyways, it has to be small because it's only in the field for a very small time because of how fast it's going. Okay, but now that I know the acceleration, could I know the radius?
Yes.
Yes, but what formula would I need?
What is it? Trying to picture my notes in my brain.
B,
Oh, guys, come on.
the field autonomous. No.
No.
Mv squared over r.
Oh.
Or you could use actually more directly A equals V squared over r for a circle. For a circle, remember this? So, r equals V squared over A, which is 1/10 C squared over 1.32 times 10 to the 18 equals. Oh, what's wrong, Lynn? You don't look happy either. Lynn, where did I get this formula from? Circular motion. Yeah. Is it? What's wrong? Don't tell me what's wrong. Something's wrong.
I don't get the QB, the B.
Oh, the force is tiny.
The B is given in the question.
The radius.
It's 250 millitesla.
6.82 times 10 to the minus 4.
Okay.
Yeah.
It should be small because of the 18 here. What you say was?
6.82 times 10 to the minus 4.
Yeah.
So basically it's CERN work.
It's how your mass spectrometer works.
So the circle is.
It's tiny. It's tiny.
So
It
it will
will.
only get deflected like.
Yeah. Like it'll it'll more or less look like it's on a.
Almost.
Yeah.
Like horizontal.
Yeah. Now the reason it's so ridiculously small is because it's the particle. I think you're never going to fire a single electron at the screen. It's going to be something that has a charge of a few electrons and its mass will be a bit bigger. Before we finish, I just want to run through the mass spectrometer. Can I scroll down? Yep. Okay. You don't have class after this, do you?
No.
No. So let's build our mass spectrometer. So stage 1, we have to accelerate it into an electric field. So we'll say it has voltage V and a distance D. Okay? And then stage 2, we have to put it through a magnetic field, north-south, and we'll say that this magnetic field has a flux density of B. Okay? So, and we'll say it begins here, Q and M, and it's at rest. Okay? Right, so firstly, I ultimately want to calculate the radius here. Sorry. The radius here of deflection. Okay? But in order to calculate the rate, okay, well let's have a look at the formulas. What do we say it was? A equals V squared over R. So then that means R equals V squared over A. Okay, well so we need to know V and we need to know A. So if I use the formula F equals QVB and MA equals QVB, now at least I have the A. So now I get R equals V squared over Q.
So MV squared over QVB.
Q, yeah, VB over M. But of course this V cancels with this V, and as you said, Zach,
MV.
it's MV over QB. Now let's just think, do we have enough information? Well, I could know the charge. You could measure the charge quite easily.
Know the velocity.
Sorry, I misspoke. The mass and the charge are the things we're looking for. I definitely could know the B, because that would be printed on the magnet. But do I know the speed here? No. So, the speed here is the same as the exit speed here. And it's at rest here, so I can use conservation of energy. So, the potential energy, what was the formula?
MGH.
No, that
So
the
it's
QV. Yeah, QV. The charge times the voltage should equal a half M V squared. So then that means that the V velocity will equal 2Q voltage over mass and root then. Okay, so let's plug that into this formula now. I get R equals M over QB root 2Q voltage over M. Now I can clean this up a little bit more because I can change this into root M squared, and so this can go inside as an M squared here and cancel it then. I can do something similar with the Q. I can make it a Q squared in a root and put it inside. Yeah?
And it's Q on the bottom.
And it's just, what's only left there? B, isn't it?
So it's,
So it's 1 over B root 2VM over Q. Now, what is it? What is the thing that you're looking for? What's it called? Is it mass to charge or charge to mass ratio?
Charge too much.
Mass to
Mass to
charge.
charge.
Mass to charge.
Yes.
Right. So let's get that. That would be RB squared equals 2VM
Mass to charge.
over Q. So that means q r squared b squared over 2v. That's equal to m over q. So you can say that the mass to charge ratio, which is this thing here. Oh, sorry. I shouldn't have brought the q up here, should I?
No, just.
Yeah, it's gone. Thank you. Is equal to r squared b squared over 2v. Now look. Do you know the voltage? Obviously. Do you know the magnetic field density?
Yes.
Obviously. Can you measure the radius?
Yes.
So from a bit of trigonometry perhaps. So by simply using this formula, you've calculated the mass to charge ratio. Okay? Now you don't need to write this down. This was just showing you how the mass spectrometer works. Wait, before you go, I have one more quick one to do. Just keep this one in your mind. Okay. So if you look at this one, if you have a drop of oil here and you put a little charge on it, what you try to do is have it balanced so it falls at a constant rate. Okay? Oh, flip. Hang on, just give me a few seconds. I forgot something. No. Yeah, okay. So, mg, and then going up here is EQ, isn't it? Yes. So you have EQ equals mg. Okay. So you can get Q equals mg over E. Now, do you know the E? You could, because you can know the voltage and the distance. So you know the E. Do you know G?
Yes.
Yeah. And then the M here you could know if this is a small little drop of oil. You know, you could know the M here. So I think in this experiment what they did was they used small drops of oil, like maybe 1 microgram, and they were calculating the charge. And then maybe they used different masses and so on.
This is when it's stationary.
Yeah, or moving at a constant speed, it's the same thing. Anyways, the point of the story is, by looking at the results for the charge required to balance it, they noticed that the charges are always a multiple of this number.
Natural.
Yeah, the charge of an electron. Yeah.
Oh,
Anyways, what I'm trying to say is, this is how they calculated the charge of an electron. Okay, they measured the different charges that you would get to balance this system, and in all the situations they noticed that the charge is always a multiple of what we call the E constant for electron charge. So then they conclude, okay, so then this must be the charge of an electron because everything is a multiple of this number. You know, sometimes it's 10 of these, sometimes it's 5 of these, and so on. So if you know the charge of the electron, and if you know the mass to charge ratio of an electron, then what could you work out? The mass of an electron. You see, I really like this because you use 2 experimental results together to calculate something seemingly impossible to calculate, the mass of an electron. Right? So if you know the mass to charge ratio of an electron, and you also know the charge of an electron, then you can know its mass. Right? And this is how they get the mass of the electron.
But then how do you convert the signal of charged particle hitting the amplifier into...
Yeah, I don't know. Like, what they might have is, they might have some screen
Yeah.
that is, what's the word, fluorescent or something? So when the electron hits the screen, they can see where it hit the screen and calculate the distance from the center, and from that calculate the radius it travelled on. It's a possibility, right?
But that impact is going to be super small. So,
Yeah, so I think you can make the radius a bit bigger if you can fire the electron faster,
okay.
you know. think this is great. I mean, how else are you going to get the mass of an electron? Do you know? Anyways, I just thought you might enjoy connecting this with your chemistry, because I doubt in the chemistry coverage of it you talked at all about the physics of it or the equations of it. Yeah, I didn't think so. Please do your homework. Thank you.
Stupid question.
Two questions.
You think you can manage that?